Okay, let's dive into this explainer. Have you ever thought about the invisible laws of physics that silently dictate the shape of our entire world? I'm talking about a fundamental rule governing everything from those massive industrial grain silos you see on the highway right down to the steepness of a mountain. And, as we'll see a little later, it even serves as this incredibly beautiful metaphor for the human condition. It's called the angle of repose, and figuring out exactly how the angle of repose works reveals a hidden geometric order in pretty much all the everyday materials around us.
To really grasp this, we have to look around and ask a seemingly simple question. Why do certain physical structures hold their ground so effortlessly, while others just instantly give way to gravity? I mean, have you ever noticed how a pile of dry sand always settles into the exact same cone shape, no matter how carefully you pour it? Or why adding just a tiny bit of water lets you build a towering sandcastle, but adding too much causes the whole thing to slide away into a puddle in literally seconds? Well, it all comes down to a strict mechanical boundary enforced by nature. And that boundary, that's the angle of repose. By definition, it's the maximum steepest slope angle where a pile of granular material can lie without slipping. You can kind of think of it as a microscopic battlefield. On one side, you have gravity, constantly pulling the particles downward along the slope. On the other side, you've got static friction, holding those particles together. The angle of repose is that exact mechanical threshold where static friction finally loses its battle against gravity and an avalanche begins. So here is our roadmap for today. First, what is the angle of repose? Second, calculating the magic number. Third, factors that shift the angle. Fourth, industrial and engineering applications. Fifth, preventing Earth slope failures. And finally, a metaphor for stability.
All right, jumping right into section 1, what is angle of repose? The exact point of sliding.
In engineering, the angle of repose and the angle of friction are actually mathematically identical. They're just described differently based on whether a pile is being formed or an object is being pushed on an incline. They both rely on the inverse tangent of the coefficient of friction. And you know what's crazy? Nature is totally well aware of this math. Take the antlion, an insect that builds sand traps to catch its prey. The antlion digs the sides of its pit at the exact angle of repose. When an ant wanders in, the slightest little disturbance causes the sand to instantly roll down, making it impossible for the ant to escape. It's a deadly physics trap.
Moving on to section 2, calculating the magic number, finding the math at home. What's really cool is how easily you can calculate this magic number yourself. Just pour a simple pile of granular material, like sugar or sand, onto a flat piece of paper from a fixed height, maybe 2 to 4 inches above the table. Once it stops flowing and settles into a cone, gently measure the height of the peak, which we'll call h. Then, measure the diameter of that circular base and divide it by 2 to get the radius, or r. By calculating the ratio of the height to the radius and hitting the inverse tangent function on your calculator, you will reveal that specific material's precise angle of repose.
Okay, section 3, factors that shift the angle. Shape, size, and moisture. Now here is where it gets super fascinating, because not all materials stack the same way. Particle shape and size heavily dictate stability. If you run that DIY experiment at home, you'll find that granulated sugar, with its small, uniform cubic crystals, settles at a fairly shallow angle, usually around 30 to 34 degrees. Dry sand sits a bit steeper, around 33 to 38 degrees, mostly because the grains are rougher and have more surface friction. But get this, uncooked, long-grain rice will form a significantly steeper slope, up to 45 degrees. Why? Because those elongated, irregular rice grains mechanically hook and interlock together, preventing sliding even at high inclinations.
But shape isn't the whole story. Moisture is a massive game changer. If you take that dry sand at 34 degrees and add just a light mist of water, it creates these microscopic capillary bridges that bind the grains together, allowing the sand to stack up to 45 degrees or even higher. That is exactly why you can build steep walls on a sandcastle. However, if you completely saturate the sand, the water fills all the empty voids between the grains. Suddenly, the water acts as a lubricant, the friction is destroyed, and the pile catastrophically collapses down to a shallow 15 degrees.
Let's look at section 4, industrial and engineering applications. Making powders flow.
So granular physics isn't just some abstract concept. It is literally the backbone of global industries. Take the pharmaceutical industry, for example. When companies are pressing pills, powder has to flow rapidly and uniformly into the machine dies. Pharmacists actually use the angle of repose as a direct indicator of flowability. Looking at data from LFA tablet presses, if a powder has a low angle of repose, say between 25 and 30 degrees, it flows excellently. But if the angle exceeds 45 degrees, the material is way too cohesive and sticky. It will bridge and clog the machines. If a mix tests that high, manufacturers literally have to add special flowing agents or agitate the machinery just to keep production moving.
Which brings us to Section 5, Preventing Earth Slope Failures, Geotechnical Life-Saving.
Scaling up from microscopic pills to massive mountainsides, engineering the angle of repose becomes a literal matter of life and death. When engineers are dealing with infinite slopes, like the long face of a mountain, or finite slopes of known dimensions, they have to calculate a factor of safety based on the soil's natural angle. If that naturally stable angle is exceeded, perhaps due to sudden water erosion, earthquakes, or excess loads from heavy vehicles, you risk terrifying earth slip failures. As our sources point out, these failures can happen internally on the face or toe of the slope, or they can be massive, deep-seated base failures, where vast wedges of earth just shear and slide away all at once.
So how do we prevent these disasters and safely build structures that exceed the natural angle of repose? Well, geotechnical experts basically have to artificially cheat physics. Companies like ABG Geosynthetics rely on intensive stabilization techniques. They use tension elements like geogrids to hold massive blocks of soil together. They drive steel soil nails deep past the potential failure planes to anchor the earth using friction. They also install complex lateral drainage systems like French drains and geosynthetic fin drains, because as we learned with the saturated sand, unmanaged water is the absolute enemy of granular stability.
And finally, Section 6, a metaphor for stability, from dirt to the human condition.
We've seen how the angle of repose governs sugar, pills, and mountains, but it also creates a really fascinating pivot into literature. Back in 1971, the author Wallace Stegner published a novel titled Angle of Repose, which actually went on to win the Pulitzer Prize for fiction. The story is narrated by a wheelchair-using historian named Lyman Ward, who's researching his pioneer grandparents Oliver and Susan. Oliver was a mining engineer who chased jobs all over the American West, while Susan, a refined artist, struggled to adapt to the rugged, unstable frontier life. Stegner brilliantly uses the angle of repose, the exact engineering term for the angle at which soil finally settles, as a profound metaphor. It represents the point where the loose, turbulent wandering of this family finally stops, and they're able to settle into emotional and physical stability.
Which brings us to the end of our explainer. We've seen how physics demands that every loose material eventually finds its resting point. Soil requires friction, interlocking shapes, and sometimes artificial reinforcement from engineers to stop sliding. It forces us to ask a rather beautiful question about ourselves. Just like the earth beneath our feet, what are the forces, the relationships, and the reinforcements that finally bring stability to the shifting sands of our own lives? Think about what creates your personal angle of repose. Thanks for exploring this fascinating concept with me, and keep observing the incredible science hiding in plain sight.